Okay, we have Adam Carlson, everybody. Thank you.
Hi there. My name is Adam Carlson, and my project was on accessibility to emergency food services using public transportation in Seattle, Washington. And I was also working with Dr. Felix Liao, who's manning the computer over there, and Dr. Mike Lowry. So what are emergency food services, and what are they used for? So we described an emergency food service as, in the context of our research, as basically a food bank or a food pantry. And a food bank is a community-led way of helping people who are facing food insecurity get nutritious food when they may not be able to. And food insecurity is the lack of a reliable source of healthy and nutritious food. So about 17.3% of households in the United States are facing food insecurity, according to 2022 numbers from the United States Department of Agriculture. And they track this over time, and generally it tends to grow when there's an economic downturn, such as most recently with the recent growth, such as you can see with the growth due to the coronavirus pandemic. And so it is a big issue, and it's one that we were trying to figure out how we could best understand a little bit better and potentially help combat. And so how we quantified food insecurity for our research was relatively simple. We used the Supplemental Nutrition Assistance Program, the food stamps program, used by the United States government, that has income requirements based on household size. So based on the amount of people within your household and your economic level, it will allow you to qualify for food stamps. And food stamps can also be used by people who don't necessarily have a permanent residence. So people who might be houseless. And so we found that that would help potentially include people who might not necessarily be counted otherwise. And the reasons behind studying Seattle specifically are the size. It's one of the larger cities within our region, the Pacific Northwest. Likewise, the proximity, it being so close, and the availability of data. Just because Seattle is one of the leading cities, at least regionally, that uses open source data. And so a lot of the data that we used was relatively easily accessible. And our research objectives were to observe the spatial temporal relationship between public transportation and food bank accessibility, as well as to use general transit feed specification, GTFS data to estimate transit time based travels, at the census block group level, and then to evaluate where there might be some disparities between being able to access a food bank and their need to access that food bank. And so one of the first ways that we went about doing this was to look at the total citywide hours of operations for food banks. And what we found was that there was a trend throughout the middle of the week, Tuesday, Wednesday, Thursday, in the mid-afternoon or in the afternoon, between the hours of 12 to 5 p.m. and that there were relatively few food banks open on the weekends, which might make food banks less accessible for people who work during the middle of the week. And the GIS method that we used was, we used a lot of GTFS data, and GTFS data is like transit feed data that is usually used as like the Google standard. So stuff that would be used in Google Maps and that kind of thing. And so the tools that we used were GTFS to public transit model, which converted our GTFS data into a usable features within ArcGIS Pro. And then we connected that public transit model to a street model that we got from the Seattle Open Data Portal. And then we used the create network data set from template tool, which then allowed us to build a network. And we then measured the closest facility from throughout the region. And so what we got, so starting from the left is a map of the food insecurity within Seattle. Generally darker colors means more food insecure regions. And the lighter the color, generally the less food insecure. In the middle is then transit access to food banks using, I believe, the median minimized travel time to food, using that closest facility tool. And then on the right side, it's a bivariate map using basically a comparison between the two, with the darker the color generally meaning less transit access and more food insecure. And we then also use that same kind of metric for distance or for travel times. And so using that same network approach, we measured the walking distance to food banks as well as the transit time to food banks. And we found that less than, or about 40% of people would be able to access a food bank within half a mile or walking distance from their household, and then about, or just over 85% or close to 85% would be able to access a food bank within 20 minutes travel time. And these are some of our conclusions. So within 20 minutes of transit time using public transportation, more than 80% of the population of Seattle would be able to access a food bank. Although this might be a little bit more restricted based on the operational hours within Seattle for food banks and whether or not they're open. And so it's not necessarily perfect in that regard. We also found that there were hotspots of neighborhoods most likely to experience food insecurity and inadequate transit support or transit access to emergency food services. And we found that those were primarily in southern Seattle. And then the conclusion or the policy implication that we came up with was that transportation agencies could potentially provide on-demand services to help people who might not necessarily be able to access these services to help people who might not necessarily be able to access these services get to the larger food banks and food pantries. And they also should maybe consider routing mobile food pantries to the most vulnerable areas. And then other applications of GTFS. So using ArcGIS Pro, there are a few different ways that you could potentially use the GTFS data. As basically using the same method that we did, you would be able to import the facilities that you were planning on using. And so one of the examples that we specifically used was tracking the same kind of figures, but instead of to food banks, to food stamp accessible grocery stores. And so there is potentially a lot of other uses for this GTFS data and this method of research. Yeah. Any questions?
I'll ask a question. From the mapping of where you have the food banks and food pantries, did you find any areas that were kind of like oversaturated or like, were redundant, where maybe there's too many in this area that aren't needed?
Yeah, we found actually in this bivariate map here, The places that are it's mostly, I guess, the transit map. I guess the map specifically is more related to transit access, but there were definitely certain places that were more saturated in terms of food banks than others that might not necessarily have access.
Any questions? All right, let's thank Adam one more time. Okay. Okay, and it looks like Jason has joined us, so hopefully he'll be able to share his screen. See his video.
Yep, can you hear me?
Yes, I can hear you.
Oh, fantastic. Okay. And you can see the screen now too?
Yes, we see it. You're ready to go.
Fantastic, great. It's amazing when technology works the way it's supposed to. All right, well, thank you, everybody. It's good to be here, and I'm glad that we have a remote option today. I wanted to just talk a little bit about a ongoing project that we've had that has kind of taken an interesting turn, and to talk a little bit about how we actually extract geographic information from scholarly literature. So how we take locations out of published scientific articles and display that information geographically. The use case that I want to start with here is what happens or what if you want to search for scientific literature from a specific place. And this is just an example of that we sort of put in a previous paper where we did a web of knowledge search for articles related to the Chihuahuan Desert. And we took all of those almost 800 articles, and then we put a pin on a map for where that study was actually conducted. And you can see that only about a third of those pins, or those yellow dots, actually occur within the sort of defined boundary of the Chihuahuan Desert. And that's actually a pretty generous boundary for what you would consider the Chihuahuan Desert. And this also doesn't represent all of the articles that are within that area that didn't use that phrase Chihuahuan Desert, right? So we're missing stuff, and we're getting a whole bunch of stuff outside of our target area. So what's really happening here? So we have a question, right? In this case, we want to know something about the ecology of the Chihuahuan Desert, and we've put that into a literature search like Web of Science or Web of Knowledge in this case, but you could be like Google Scholar. And we're going to run a search on that, and we're going to get some results. And these results are going to be relative to the theme or the topic of the question that we asked. But if we're interested in a specific place, then only a small subset of those results are actually going to be relevant to that location. And so our sort of proposal here, or the sort of goal of what we're driving at is, let's do a geographic-based search for scientific literature so that we get stuff that's specific to the topic and the question that we asked, but also specific to that area. And then what makes it really powerful then is if we have it sort of, geo-enabled, right, our search, geo-enabled, then we can actually search for information that's from similar geographic areas, right? So it might be relevant to our question based off of the contextual similarity of what we have. And so this is kind of the sort of the use case or the impetus behind the journal map search engine that we created. And it is a geographic literature search engine. You can go to journalmap.org. You can search through there. There's about a little over 30,000 articles in the database right now. They're really heavily focused on arid lands ecology because that's sort of what I do. And you can search by keyword, you can search by area, you can look at sort of different environmental filters to try to pick out stuff from similar areas. And it's really designed to help you find the stuff that's relevant to the questions that you're asking in the specific locations. But there's a problem or a challenge with this, which is how do we get the content into Journal Map to enable this geographic searching? And it turns out that that's actually fairly challenging. Even with 30,000 articles in Journal Map, that's sort of a novelty, right? It's not an actual like robust data set for searching. So what we found through Journal Map is that the majority of articles from sort of the ecology or agriculture domains are specific to places, right? So more than 90% of the articles that we've looked at do have a study area that we could identify on a map as either a point or a polygon. But there's just enormous variability in how those are actually reported. Everybody's describing them with some sort of place name designation, but only about half of the, I don't know why my slides are auto advancing, only half of the studies are actually reporting any kind of coordinates. And that poses a real challenge for us in how we're actually going to geotag these articles in any kind of automated way. If we have coordinates that are actually reported in the paper, we can extract those with a very high degree of accuracy. The current geoparser that we have in Journal Map, which is this sort of really ugly regular expression that you can see in the background, we can recognize about 80 different coordinate formats, pull those out, and then convert those to pins on a map for Journal Map. But that's covering less than half of the articles that we're looking at. And so we still need to figure out how to do geotagging based off of place names. And this is something that any one of us could look at and within a matter of seconds tell where a study was done. But in terms of doing it programmatically, ends up being extremely challenging because of irrelevant place names in articles or the use of uncommon or non-standard place names or things that look like place names like Canada goose or any of the species names that have an area or a location in the name. How do we do that? And we originally, in kind of an earlier iteration, looked at some natural language processing tools to help with this and to build a workflow around automating the sort of geotagging of scientific articles. And I'll just say that generally the results were less than satisfactory. The best tool that we used was Mordecai, which actually uses a combination of a number of different tools. But even Mordecai was only about 65% accurate. And this is off of a set of 120 articles from PLOS One that we had confirmed locations for those articles. And so accuracy was defined by whether or not a location was identified by one of these tools and if that location was within 100 kilometers of the actual location. So that's a fairly generous definition of accurate to begin with. So what we kind of concluded from this was that none of these tools really were buying us much in terms of automating the geotagging process because we didn't feel confident that we could actually get good place locations to feed into a location service like Journal Map. Okay, so but about the time we were wrapping this up, a lot of the tools like ChatGPT or these other large language model AI tools were really starting to take off, and so we started to kind of wonder if we could use any of these new tools to automate this geotagging process. So we used the same set of 120 papers from PLOS One. You can see the map here shows the locations of all of those studies, the confirmed locations. And then we took a subset of these articles. We're working on this, it's in progress. We will eventually do all of these articles, but for now we've got a subset of these articles and we've run them through 3 different tools. So ChatGPT 3.5, BARD, which is Google's large language model, and then one by Anthropic called Claude 2. And we used the downloaded PDFs for these articles and uploaded the PDFs into the tool, and then asked it a series of questions. Is this study specific to a location? And if the answer was yes, then where was that location, and give us coordinates in a CSV format. And so from the results, we were looking at three things, at least initially. So the number of articles where it could actually find a location and return a location to us. The average distance from the location that it returns to the confirmed location that we have for these studies. And then we did a little bit with looking at repeatability. So if we asked it the same question multiple times, how similar were the answers? And just kind of in brief, really, we found that these tools did quite well. All three tools returned locations for all the articles, or for like the majority of the articles. Obviously, from what I've highlighted here on the slide, you can see that Claude was the winner, just sort of in all of these criteria. It returned locations for 95% of the articles, and accurately located 95% of those articles as well. And that is that accuracy definition of within 100 kilometers of the confirmed location. When we looked at the average distance from the confirmed location for Claude, the average was 33 kilometers. And I should point out that there are a handful of studies that the distances are large, like in the couple hundred kilometers, but then there are also a lot of studies from Claude where it got the exact location right compared to the confirmed location. So the distance was 0. So Claude was performing quite well. ChatGPT and BARD did pretty good, but nowhere near as good as Claude did. And then you can see on the right-hand side, like the prompts that we asked and then the results that we got. Certainly we're finding, and there's a lot now that's coming out about these tools that a lot of the success of these tools is dependent on how you structure the query and what kinds of questions that you ask. But what we've come away with so far is feeling very optimistic that a tool like Claude can actually help us build workflows to automate this. So the next steps here is going to be building this into something that uses an API interface rather than the sort of web interface for these tools, and then extracting the results out of that to automate that process. Looking at the repeatability, these are generative AI tools, so it's not looking up the result, it's actually trying to determine the result from the text that you give it. And so on subsequent asking of the same question, you may get a different result. So we picked just a subset of 10 articles, and we asked the question, where was this study conducted? We asked that question 10 times for each of these 10 articles. And we did a sort of an average or a bounding box, an oriented bounding box for all of the answers, and then kind of looked at the dimensions of that bounding box as sort of a proxy for how consistent those results were. And another interesting thing we found too is that if you ask a question, where was the study conducted, the tool may come back and say it couldn't determine a location. But if you ask the question again, it may actually find a location in there. So just because you got a no the first time doesn't mean you'll get a no on subsequent requests. However, we did find that, like BARD, and one of the issues we had with BARD in terms of performance is that it tended to give us spurious results. So the map on the bottom, you can see this one study was in a region sort of southeast of Paris, France. And by and large, most of the dots show up in the right area, but for BARD, one of the times we asked the question, it actually came up with a location of Moscow, Idaho, which does not show up anywhere in that document. So we're not entirely sure where that came from, but it did code that as a result in there, and that throws stuff off. So I think there's take home here is that there's some work that still needs to be done to sort of filter or vet the results. So again, we feel really sort of optimistic about these tools to extract locations from unstructured text and to build those into workflows that can feed into search tools like Journal Map. And so with that, I'll take any questions.
Hi, Karl. Really interesting presentation and fantastic work. I have a quick question about you mentioned why you mentioned 3 different large language model, BAR, ChatGPT, and Karl. Why that the third one is the best? Actually, sounds like the big companies do not create good tools.
Yeah, I'm not 100% sure what the differences are between the 3 of them. I think it has to do a lot with like how many parameters they're trained on, and one of the issues with ChatGPT 3.5 is that it doesn't have access to the internet to be able to sort of look up results or cross-reference results. ChatGPT 4 does. We had already started down the road of ChatGPT 3.5. I think we're kind of interested in repeating it with ChatGPT 4 to kind of see if it has any differences there. But yeah.
Yeah.
Just because with the work that we do, we're using natural language processing, and having 120 points isn't nearly enough to train Spacier and an LTK. Did you try training it across all 30,000 to see if you can get results that actually are correct?
For the natural language processing tools, we didn't use the PLOS data to train the models. We used the pre-trained models that were available from the entities that created them. So these were all pre-trained. They weren't anything that we trained. We were just running these models on the article set that we had. One of the reasons that we used the 2 different versions of Spacie was to look at differences in how models were trained. I think one of our conclusions from this was that there's potentially a lot to be gained by training a specific model, but that was kind of beyond the scope of what we were trying to do with this sort of implementation. And to be honest, given the results that we've seen, like with Claude, I'm not sure that it would be worth the time to train one of these models compared to investing in more of a customization of a large language model.
All right, let's thank Jason one more time and move on. All right, our next speaker should also be remote. The US.
Yeah. Okay. No.
I think he's got a promote. I think so.
Hello, can you hear me all right?
Yeah.
Okay, awesome.
How are you doing today?
I'm doing well, thanks.
Well, I got to turn this microphone on. It's been the bane of my existence today here. It seems like I can't get it right. Okay, so our final presentation for the day, invited speaker with us today is Phil Roberts, who actually is a graduate of the University of Idaho, which is great. And he is the National Remote Sensing Coordinator with the Farm Production and Conservation Business Center, known as FPAC-GEO, I think is the acronym there, with the US Department of Agriculture. So he's going to talk to us about a land change analysis tool that they've been working on. And Philip and folks online, I think we're set to go. So we are good for the next 25 minutes or so.
Awesome. Thank you for the intro. Yeah, Phil Roberts from USDA FPAC-GEO. Today we'll be talking about the Land Change Analysis Tool, or LCAT. Because this is government, it's all acronyms, so just get used to it. I'll do my best to kind of fill them in as I go. So what we've done is developed a machine learning algorithm to produce land cover maps from aerial imagery. So we'll talk a little bit about the background, sort of the why, then we'll get into the methodology, we'll talk about how these are made, and then lastly, we'll talk about some of the cool applications. Okay, so in the Farm Bill, most recently updated in 2018, there's specific language about program accountability and integrity. Data mining to identify changes, right? Looking for waste, fraud, and abuse in government programs. There's a lot of language about that, and government oversight's an important topic. So that's sort of where we come in, right? We're developing a tool to help make this compliance easier. So a lot of that is centered around CLU, or the Common Land Unit. That's something that's produced at FSA, the Farm Service Agency within USDA. And those are field boundaries that contain, crop information, what was planted, when it was planted, producer information, that type of thing. And within FSA, they have policies such as 10CM that goes into, what's included, what's excluded, how do you digitize these things, how are you supposed to update them? And that's really the genesis of NAPE imagery, the National Agricultural Imagery Program. That's something that we produce in our shop at FPAC-GEO. I hope a lot of you are familiar with that. It's a very valuable data set. So NAPE was generated as a compliance tool for FSA to help them check their CLU against the latest aerial imagery. If someone says they're growing corn and there's a chicken house in the middle of the field, that's not in compliance, right? That's something that FSA is going to want to know about. So the real challenge here is that in the CLU database, there's about 39 million records. And at FSA, they have about 5,000 county office staff who are tasked with generating, maintaining, updating all the database work that goes into keeping up this gigantic data set. And every time new imagery is flown, which is every 2 years roughly, they have to do that process all over again. So it's very labor intensive. The bottom line, USDA is a customer service agency, right? If you have a lineup of producers out your door trying to sign up for the latest program, you're not going to turn them away to do back-end data management work. So typically this is sort of fallen by the wayside. And that's where the need for LCAT was born. So 2018, 2019, this really got started, and we've been kind of running ever since. So now I've told you the why, let's sort of get into the methodology. Really, I think of this as a six-step process: scoping, sampling, labeling or training, mapping, and then publishing, and lastly, the analysis, right? What can we do with this? So we'll quickly walk through all this to show you how these maps are made. Another important takeaway here, this graphic, this is an iterative process, right? We're going to map states multiple times. So every time we do this, we learn more. We try to get better at producing high-resolution land cover maps. So we start off with a scoping session. This is where we meet with local staff from FSA and NRCS to kind of get a handle on what's going on in the state. Here we've got South Dakota as an example. So when we develop our sample plans, which you see on the left here, we look at a variety of input sources, right? We look at the National Land Cover Database. It's a great place for land cover information. That's produced by Forest Service and USGS. based on Landsat data, and it has a 30-meter pixel resolution. Another thing we like to look at is the MLRA, or Major Land Resource Areas. These are developed by NRCS Soil Survey, and they represent areas of homogeneous soil forming factors, right? So if you think of those as bedrock geology, topography and relief, climate, organisms, right? Forest, ecology, plant communities. All of that stuff is going to have an input on soil type. And fortunately for us, that also has an input on land cover. And then lastly, we're going to look at properties that are sort of intrinsic to this NAPE imagery. Stuff like seam lines, where we can see the individual flight paths that the airplanes took as they collected this imagery, and how those are dated, how they vary throughout the season, right? That's important stuff for us to understand as we look to classify this imagery. So this is definitely sort of the art to the science. We look at all of those different layers, and then we try to build a sample plan that identifies sort of homogeneous regions. And South Dakota is a great example of this, right? You have the Black Hills of South Dakota, primarily ponderosa pine forest. It looks nothing like the rest of the state. So we're going to break that out. We're going to treat that as a separate mapping unit than something you'd find on the eastern side of the state, where it's more humid and more agrarian. This MLRA concept was really a light bulb moment for us. We started mapping in Alabama. We were working closely with a state GIS specialist down there. We mapped our first county. We said, okay, can we do the next one to the north? Yeah, go ahead. How about one more? Yeah, go ahead. How about one more? No, that's different. They have a different kind of grass up there. I don't know anything about Alabama. I've never been there. I don't know about the grass there, but Sean does. And when he told us that, and we realized it lined up perfectly with the MLRA map, that's when we kind of knew we were onto something. So that's step one. We develop these sample plans. In step two, we generate sample points based on those sample plans. So here you can see what that point looks like from Gregory County, South Dakota. You can see this looks different than the rest of the state. We focused on this area for a specific project that you'll see later. We use an algorithm called conditioned Latin hypercube sampling to do this. What that does is it looks at the 4 bands of NAPE imagery, so red, green, blue, and near infrared. We also calculate an NDVI layer and stack that back in, and those are our 5 inputs. So it looks at those 5 inputs and comes up with distributions of each of those and picks points iteratively that fall into every bin of every predictor variable. So that's what CLHS is. That's how we generate points from imagery for sampling. Next up is the training step, right? We take all those points, we throw them into a custom-built ArcGIS web application that's available in ArcGIS Online. This allows us to sort of crowdsource this massive task of model training. So you can see our app here. This was from Montana in UTM Zone 12 with 2021 imagery. Based on where a point falls, you will assign it a label of a land cover class, and then the app automatically takes you to the next point. It's a pretty slick tool. You can see at this zone of Montana, we had about 47,000 points labeled. This is a very large data set. We hope to shoot for about 10,000 points per week. I know when we were ripping through Idaho the first time, we were doing closer to 15,000. It just depends on who's around. I know that number is going to be going down as the holidays approach. But being able to crowdsource this is massive for us. It allows us to partner with universities. We've had good success with that in the past. This is what drives the whole thing, right? The rate of labeling is what governs the rate of mapping, which is our next step, mapping. So once we have that training set, we've got NAPE imagery, we've got an observed land cover class, we're ready to start modeling. We're using random forest implemented in RStudio, and that allows us to produce these land cover maps. NAPE imagery, the fundamental unit is a quarter quad, and depending on the resolution of the imagery, there's about 125 million pixels per image, not to mention those are 4 bands, right? So this is a huge data set, right? This is definitely big data. And one of the things we've done to help us with processing is implemented Docker containers. So by containerizing this workflow, it allows for horizontal scaling. We have a 192 node cluster where we can distribute this processing. That was huge for us. The first time we mapped Georgia, it took us 3 months. I had 2 empty cubicles full of laptops that were humming along as much as I could keep them running, and that took us about 3 months. The second time through on Georgia, we implemented our Docker cluster and we mapped the whole state in about a week and a half. So significant production improvement there with our Docker cluster. So let's look at some of these maps, right? This is the cool part. Here you can see 3 different things. In the middle, we've got NAPE imagery from 2021. On the left, you can see the National Land Cover Database. Again, this is a satellite product from Landsat with 30-meter spatial resolution. On the right, you can see an LCAT map with 60-centimeter spatial resolution, right? That's 2,500 times the resolution. And a colleague of mine came up with a great analogy for this, right? A 30-meter pixel, that's pretty darn big, right? That's like a large room, maybe the conference room you guys are in today. A 30-centimeter or a 60-centimeter pixel, that's a foot or 2, right? That's a pretty significant improvement. And you can really see that here in the imagery where we're able to pick out little grass strips within parking lots or thin sidewalks that you'd never be able to see at a coarser resolution. Here's another example from Connecticut. I believe this was in 2016. You can see sort of some forested landscape with suburban developments and some farm fields. Here's what that looks like at NLCD. Here's what that looks like at LCAT. Pretty significant difference in terms of spatial resolution. I really like here how you can see that little grass strip in between the sidewalk and the road. So where have we worked so far? States in green have been completed. Some of them have been completed multiple times. States in pink are stuff that's ongoing. So I know we're training in New Mexico right now. We've scoped and sampled a few of those other states. They're all in various pieces of the workflow. You can see the volume of our training data here as we started this late 2018, early 2019 till now. We've developed a library of over 1.2 million points that have been labeled, and we've mapped over 1.2 billion acres. That training set, I think, is one of the most valuable things we're producing. The maps are great. The training data is so much more valuable because as new classification algorithms become available, we have this really robust training set that we can use to evaluate them. So we take all these maps and we publish them into web map services, specifically image server services. These are available to the public. That's the URL right there on the top. Here's just an example of a few years of data. I think we've got over 20 states published so far. More are in the works. We had a meeting on that this morning. So we'll continue to get more of our data publicly available. And then one of the newer things we've created is a best available image service where it sort of combines all these individual years and filters out the latest and greatest imagery classification for your state. So very valuable tool there. So lastly is the analysis piece, right? We can make these maps, but so what, right? What can we do with them? That's where this gets really important. So I'll show you a couple examples here. Farm Service Agency, again, FSA, NRCS, those are the FPAC agencies, right? FPAC is FSA, NRCS, and RMA, the Risk Management Agency. So those are our primary customers. We also work closely with the National Cooperative Soil Survey. We've worked with USDA APHIS and a couple other academic institutions such as University of Maryland. So first, I want to start off with the FSA example because that's what really got this whole thing off the ground. We mentioned that Common Land Unit Database, or CLU. So what we've done is we've built custom Python scripts to compare what's in that polygon to what's in our land cover map. There's a nice cartoon version of this on the right. You see a cropland CLU polygon. You compare that against the LCAT land cover map, and you can flag areas that don't match whatever the land cover designation should be. So here's an example of a dashboard we built to highlight this. You can see The polygon in question is predominantly forested. It was classified as cropland. Clearly it isn't. It's about a 92% misclassification rate. Our idea with this tool is that an FSA state GIS specialist could scroll through sort of a ranked list of potentially incorrect CLU and within seconds say, yes or no, this needs attention. And if it does need attention, then we can develop that sort of curated list that would go to the county office where they could start making those edits and fixing it. So here's an example of one of those. I mentioned the chicken house thing earlier. Here's a field that was certified as grass. You can tell they put in 6 chicken houses. That's the kind of stuff that really jumps out in our imagery. That stuff gets flagged, it gets back to the office, and they make the changes to the CLU boundaries, right? That's what this is supposed to look like in the best case scenario. One of the really nice things about this, those Python scripts can screen bulk records, right? We can do 700,000 CLU records, no problem. Whereas, the county office employee has to look at each one of them individually. So if you're looking for that needle in the haystack, we're trying to give you a metal detector to help. We estimated this is about a 70,000 hour workload every time new imagery is flown. And we think we can get that down under 700. So pretty significant, 100 times improvement in the efficiency, not to mention that if the records are right, the payments are right. So the farmer's happy and so is the taxpayer. Next example I want to show is from South Dakota. NRCS in South Dakota was interested in eastern red cedar monitoring. So you can see a couple pictures of that tree up there. We applied the LCAT land cover method to produce land cover maps from NAPE imagery, but we also went back in time. GEO holds a large archive of USDA's aerial imagery that we've started collecting, I believe, in the 40s and 50s. So we have imagery for the nation going back 70 or 80 years. That's an incredibly valuable resource. So for this project, we went back to the NHAP historical imagery from 1984, ran it through the same classification process. And, one of the nice things about this part of the world, it's pretty arid. There's not a lot of trees. So when you do find them, we were pretty confident that we were mapping eastern red cedar. Our initial maps have 8 classes. We made a special derivative product here that was forest versus non-forest to really sort of focus on those eastern red cedar areas. And you can see what some of this looks like. 1984 versus 2021, pretty significant change in the extent of eastern red cedar within Gregory County, South Dakota. Talking to local staff there, they estimate it takes about $1,000 per acre to control this stuff. If it's really thick and encroaching on your rangeland and you want to get rid of it, you can burn it, or you can get in there with a tractor and rip it up. Roughly $1,000 an acre to maintain. We identified about 1,000 acre per year increase, which could potentially be up to $1 million per year to maintain current extent, right? That's a pretty significant concern, and that's something we can really quantify through these methods. And lastly, South Dakota is not the only person who cares about this. People from Idaho have asked us about this. People in Oklahoma have asked us about this. So as we continue to develop more LCAT mapping, we're still acquiring NAPE imagery, and our NHAP orthorectification coverage is expanding. That allows us to sort of extend this analysis to other parts of the country. So lastly, I want to talk about some applications with APHIS, the Animal Plant Health Inspection Service, and the University of Maryland. APHIS has something called the Airport Wildlife Hazard Management Group, and their name says it all, right? They are in charge of protecting our skies by keeping birds and other wildlife away from airports. When I first heard about this, I had no idea that USDA did that kind of stuff. But they said, hey, land cover is really important for us. And if you can give us better land cover maps, that'll help us do our jobs better. So here you can see, NLCD versus LCAT, that resolution difference, again, just jumps right out at you. You can see all the taxiways, little grassed areas in between runways, all that kind of stuff. So we started working with them in 2020. We've had a couple student interns. We've had sort of small group, like 6 to 8 students working on senior projects. We've had a fall GIS class that did statewide mapping for Maryland and Delaware. Initially, we started looking at Dulles, Reagan, and Baltimore, Washington airports, sort of in the DC metro area. The following year, we did a deep dive at BWI, where we looked at 3 years of imagery and sort of saw how things changed. And then we expanded to Naval Air Station Patuxent River, which is in southern Maryland, and Kahului Airport at Maui, which was a really interesting case. They're not so much worried about birds there as much as they're worried about axis deer, these small deer that live right around the runway. Pretty interesting land use situation out there. One of the great things about these partnerships, the students are excited about it, the professors excited about it. It's great for us at USDA. It's really a win-win-win all around. Esri and APHIS conducted a separate economic analysis of this study and found a over 900% return on investment here. So just a great opportunity all around. I love this figure. This was produced by the students at Maryland, showing changes at BWI Airport over time. You can see the extension of runway 15R that was done between 2010 and 2014, and the expansion of Concourse E that was done between 2011 and 2017. Right, this is the stuff that they're able to pick out from our land cover maps by comparing multiple years. And really, the so what of this, this is a great image. This was an inbound flight to Baltimore from Iceland, and it was during our period of study. They ingested a flock of geese into one of the engines. Fortunately, they were able to land safely. Nobody was harmed. But that's pretty, it's a pretty expensive jet engine to have to rebuild. So this was one example where everyone landed safe. Another one, think of the miracle at the Hudson. These things happen. And because APHIS does their job so well, we don't think about it very often. But in sort of, through APHIS and by extension, we're trying to make air travel safer for everyone. So future goals and objectives, what's next for the team? We're going to explore more business applications, right? We just had a new request today from FDA. They're really interested in monitoring cattle feedlots, right? That's something we can pick out from imagery. We can go ahead and map that with them. Continuation of partnerships and cultivating those relationships. Last year, we had our first internship with Texas A&M University, Kingsville. They were looking at Naval Air Station, Kingsville. A T-45 Goshawk jet hit a black vulture. The plane was lost, pilot ejected and was safe, but that's a very expensive aircraft. So they were interested in trying to apply these methods there to help reduce those harmful wildlife airplane interactions. Next up, process refinement. We're always working to improve our methods. We've been working with the folks at Esri for the past 2 years on exploring sort of the latest classification algorithms using deep learning and convolutional neural networks. I've had some interesting results there. We'll continue to work on that, obviously trying to make the best, most accurate land cover maps we can. And then lastly, just on a production side of things, we're really kind of honing in on our first coverage of the country. And as more imagery is acquired, we'll continue to map more and more land cover. So that's all I have. Again, there's that URL if you want to check out any of our land cover data, and I'm always happy to answer any questions. Thank you.
Okay, let's see if we have any questions online or in the room. Anyone? Phil? We have one up front. Let me get the microphone. Hang on.
Hi. So several times today we've used this term labeling. Is this what we mean by attributing? Are we just saying what something is? What is meant by labeling?
That's a great question, and it will really depend on your application and who you're asking. But for us, what that means is generating training data that we can feed into our machine learning models. So we look at a point, we have imagery underneath it, and then we assign it a land cover class depending on where that point lands. So barren, crop, forest, grass, shrub, urban, water, or wetland. If it lands on a building, we're going to call it urban. If it lands on a tree, we call it forest. So that's what we mean when we say labeling.
Okay, so my next question is, so you can classify a shrub versus a grass. Can you classify different types of vegetation?
Great question. In the South Dakota example, I mentioned we were able to map eastern red cedar. That's sort of a unique situation where, Black Hills excluded. There's not a lot of trees in South Dakota. And if you do find one, and it's not in the Black Hills, and it's not in a river stream bed, there's a good chance that it is eastern red cedar. As far as like picking out Doug fir from ponderosa pine, that's much more challenging. And part of that is a limitation of the imagery we're using. The NAPE imagery we use has 4 bands. We add NDVI, so we have 5. If you use something like Landsat or Sentinel, you have much more spectral resolution. You can see that mid-infrared and shortwave infrared and even thermal infrared. And those, non-visible wavelengths are really important for that species differentiation. So that's not something we do a ton of. But again, our kind of rule of thumb is if you can see it in the imagery, we can probably map it.
So my guess is in the future, you'll be able to distinguish vegetation types better.
Hopefully, again, that's a limitation of our source imagery. If someone wanted a specific map of a given species, we would look at the entire set of imagery that's available to us.
Thank you.
Yeah, thank you.
Other questions in the room or online? We've got one in the back.
Is the land that you're doing based on just the CLU area, or is it the entire state?
Entire state. Yep. Which, brings up some interesting challenges, right? Stuff like snow and ice. We know that exists, but nobody's farming it. So some interesting challenges there.
Okay, any other questions? That might do it. Can I one question on this while we're on this labeling slide? Is this point data set, did you say that this was available as a web service along with the LCAT data?
No, so the land cover maps are available as an image service. We have the points, and if people are interested in accessing those, let us know. We're happy to share.
Okay. Okay, I think that wraps it up. Thank you so much, Philip. We really appreciate it.
Thank you.
Okay, that wraps up today's events, folks online and folks in the room. Thank you so much for joining us virtually or coming out in person here. For those traveling, safe trip home, and we'll see you, I guess, possibly, if you could make it to Post Falls in May for sure, other events online or in the region or here next year. Thank you very much.